Welcome friends. In today's lecture we are going to discuss pressure vessels for the point of view of PSU and gate. So let us very first start with the classification of pressure vessels. Pressure vessels are divided into thick and thin depending upon the ratio of diameter to the thickness. We will classify whether it is a thin or thick. Let us say if diameter by thickness ratio is greater than 20, then we will call it as a thin. And for diameter to thickness ratio is less than 20, then we will call it as a thickness. In this case, it says that diameter is very large as compared to thickness, so ratio is larger. That is greater than equal to 20. So again, thin pressure vessel is divided into cylindrical and spherical shapes. Thick pressure vessel is not in our syllabus, so we will discuss only thin pressure vessel. Now let us define what are the Hooke stresses and longitudinal stresses. Hooke stress is in the direction parallel to the cross section, which is perpendicular to the longitudinal axis of a cylindrical pressure vessel. That means if parallel to the cross section, let us say this is the cross section, and parallel to this is the longitudinal axis. Parallel to this means like this, or perpendicular to longitudinal axis. Here you can see perpendicular to the longitudinal axis. But for clear vision, I will draw a cylinder here. Let us say this is the cylinder, like this. If I will cut from here, not from here, for seeing these stresses, I have to cut like this. Okay. Then what will I get if I look from this side? I will get a shape like this. Okay. Like this. And these stresses will be in this direction. Similarly to this figure. Now we will call this as Hooke stress. What we will call it as Hooke stress. Let us see, here is some pressurized fluid is there, gas or anything liquid. It will exert pressure in all directions from the inside of the cylinder. Now this stress is generated to counteract this pressure force. The force due to pressure is nothing but the Hooke stress. Okay. Now it is also called as circumferential stress. As you can see, it is present all over the circumference, but not in direction of the but in the direction perpendicular to the axis. That means if this is the axis, let us say I am drawing here perpendicular to the axis in all over the circumferential area line. If I will cut a cross section, I can find like this. But for calculation, this figure we will use. How to calculate the Hooke stress? You know that this Hooke stress is counteracting the force due to pressure, inside pressure. So we will calculate this inside pressure, force due to inside pressure, with force because of this resistive stress, resistance due to the inside strength of the material. Here you can see on the next slide. You know that this is the inside pressure. We will equate this pressure or force due to inside pressure with force resistive force. That means the force which creates internal resistance or stress, internal stress inside the material. This is the inside the pressure vessel. That means here, and stress will be generated in this area. That means if this is thickness, in this area there will be a resistive force, and from inside there will be a applied pressure force applied by the internal fluid. So you know that the resistive force is equal acting on these two surfaces. Here you can see here one and here second. So F1 plus F plus F twice F is equal to pressure force. How we will calculate pressure into area, and on which area this pressure force is acting. You can see that if this is the cross section taken along the longitudinal axis, let us say on this complete area there is a pressure force acting. We consider pressure, you know that pressure is nothing but the force upon area, and this area we consider the perpendicular area on which force is acting. Let us say this force is acting like this. So this is the length L and this is diameter. Right? You can consider it is the shape of, let us say, cylinder. We have cut it into two halves along the longitudinal axis by taking section along the longitudinal axis. So let us calculate this. Projected area will become then L into D. This is D. L into D. This area. And the area in which stress is generating, you know that stress is generated. I have drawn this figure like this. This is the thickness. Okay. This is the thickness T. Here also. And you know that this complete area from here to here, like this. In this area, there will be in this area, these stresses will be generated in this direction. Hoop stress will be like this. Okay. So I have to find out this area. This will be thickness T into L, isn't it? This length is L from here to here, and thickness, you know that thickness is T. Therefore T into L. This is the area, and you know the stress is hoop stress sigma h. Now equating these on both sides, LL will cancel and you will get this equation for the hoop stress in cylindrical pressure vessel. We will also find it for spherical pressure vessel. So keep this figure or formula in mind. It is PD by 2T hoop stress. Finally, we will find in whether cylindrical pressure vessel or spherical vessel. In which vessel the hoop stresses generated will be higher. So first complete the design of cylindrical pressure vessel. We have find out hoop stresses, that is circumferential stress. Now we will find the longitudinal stress or axial stress. Then again here we will cut from somewhere here, and the final circumference can be like this. If we will straight the curvature by cutting somewhere here, and if I want to find this length of the curvature, it will be pi d. You know that circumference of a circle is nothing but the pi d. This internal diameter is di and outer is du. Here you can say as thickness is very small, you can consider di equal to equivalent to DO, right? If there will be a very high thickness, then there may be chance like we would have got such a area, cross-sectional area of a material of a pressure vessel. But you know that this thickness is very small, even though you are able to identify it here, but in practice it will be very small, so we consider DI equal to DO, and that is the difference in the thick pressure vessel and thin pressure vessel in the design of these both pressure vessels. So resistive area is this. You know that area here I can calculate D. I can consider it as a rectangular surface if I neglect this difference. Let us say DI equal to DO, means this length is equal to this length and thickness is T. Then D into T, we will get the this complete is pi D. This complete is pi D. So pi D into T, we will get the resistive area. That means the area in which stress is produced due to the strain or the applied force exerted by the pressure. Now equating this resistive force and the force due to the pressure. Again, like previous case, resistive force we will equate with the force due to pressure. You know that resistive force is 2 into F. Here area we have calculated pi D into T, and the stress generated will be longitudinal stress. And projected area, you know that now projected area will be like this. If this is the cylinder, this much will be the projected area. Now pressure will exert force in this direction perpendicular to this circular area, and we know that the area of a circular section is pi d square by 4. This is actually a DI, internal diameter we are considering. Okay, more precisely you can write here DI. Okay, here we have got the value for longitudinal stress, that is equal to PD upon 40. If we will compare this hoop stress and longitudinal stress for the cylindrical pressure vessel, you will find this is lesser than the hoop stress. Hoop stress is PD by 2T. So we can also say that hoop stress is more and longitudinal stress is lesser. Than how much it is? Hoop stress, longitudinal stress is twice that of the twice the longitudinal stress is equivalent to the hoop stress, right? Here if I write the formula, PD by 2T was the hoop stress, and here I will draw PD by 40 to 4, 2 to the 4, so that I will get both sides similar. Now this was all about the cylindrical pressure vessel. Now we will design the spherical pressure vessel. Before that, I would like to say, if there is a given problem, in the problem there is given condition is that allowable stress, let us say allowable stress is greater than equal to less than equal to 100, then we should design a pressure vessel for this much value of a stress, so that we will compare with higher stress or lower stress value. That means, should we consider it compare it with the longitudinal stress or a hoop stress, we should compare it with the higher stress. If design is safe in the higher stresses, that means it will be safe for the lower stresses also. Once it will fail in the higher stresses, then we can say design is failed for entire hoop stress as well as longitudinal stress. So we will compare given allowable stresses with hoop stress in case of cylindrical special vessel, or simply you can remember that every time we will compare given allowable stresses with hoop stress, whether it is cylindrical or spherical pressure vessel. Now start the spherical pressure vessel. You can see here this red hashed portion is nothing but the projected area, and its area can be given as pi d I square by 4. And here actually this is a force due to the internal resistance of the material, that is due to hoop stress. This is not the pressure. Actually this is, I can write like force F. I should write force F, and pressure is, I will show here, pressure by this. This is the pressure force which is acting on the inside diameter. Okay, P, like this. Now again equating the resistive force with the force due to inside pressure. You know that on the area where the pressure force is acting is nothing but this projected area, and the area which is resisting the applied force is this much on this circumferential area. How we will calculate it? Again similarly, circumference into thickness. You know that circumference is pi d. Again di is nearly equal to do, so pi di into t. This is the circumferential area into hoop stress, right? And again force due to inside pressure is nothing but pressure into the projected area. Projected area is this much into the pressure. What we will get by equating, we will cut this di. Finally we get PD upon 40. Now again we will compare this with the hoop stress in the cylinder or cylindrical pressure vessel. What we have got in earlier design for the cylinder, hoop stress was equal to the PD by 2T, isn't it? Hoop stress was PD by 2T, and here it is PD by 40. That means stresses generated inside the cylinder are more as compared to hoop stress. So always we should use a design of a shape, spherical shape. But you can see when you see on the roadsides the pressure vessels which carry petrol or any gas, they are generally cylindrical, not spherical. The reason behind that is the stability. To carry a spherical shaped vessel, it is difficult as compared to cylindrical shape. So if there is a transportation, then we will go for this design. Otherwise we will go generally for the spherical pressure vessel. Finally I would like to say why we use the pressure vessel. Why don't we use only simple vessels in which we store water like this? Because by creating pressure on these gases or converting it into the liquid, or we may not be converting in liquid if already there is a fluid like petrol which occurs in the liquid phase. If we want to store it in a vessel, and if there is a inside pressure generated due to evaporation, let us say petrol is evaporated and it creates a pressure from the inside. So to withstand that pressure, we design this pressure vessel. Or in case if you are storing, let us say, LPG, you know that liquefied petroleum gas. This gas presently occurs in the vapor phase, but we pressurize it up to a large limit so that it get converted into liquid. So that in the same pressure vessel, in the same volume of the pressure vessel, we can store more gas or more fluid. That is the use of this pressure vessel. I think, discuss all these things. If allowable stress is given in design problem, then equate it with the maximum stress, and generally maximum stress is hoof stress. So blindly you can compare the allowable stress with the hoof stress, whether it is a cylindrical or spherical. Thank you for watching this video, and even though if you have any doubts, you can write in comments. I will try to answer it, and you can also watch our previous videos on strength of materials, which includes the SFD, BMD, then torsion and stress strain, simple basics. Thank you.